Okay, we have hard problem today. So given string A, B, C, D, and this is a palindrome, by the way, G, F, E, G, C, D, A. Want to find permutation of the letters, so this gives us another palindrome that has its place in the case position if we have all the palindromes from the first smallest permutation to some x permutation. We want to find exactly case permutation, and the permutation is that we split this palindrome, have the letters, characters, and we swap these positions, obviously symmetrically for the right, and we want to achieve the smallest, or not the smallest today. Today we have case, so exactly k position in all the permutations. And obviously we have this. This could be made possible because the initial is a palindrome. We just have to permutate this left half of the string. Actually, let's look at the condition. So yes, this is a palindromic string. Okay, what should I say? I failed this problem, but not because I didn't know what to do, but because I didn't know how to write it. And actually I studied this problem yesterday, so I kind of was prepared for this solution and still failed. So this is what the hardness of this problem. It was 14% acceptance rate yesterday, but today it is almost 30 at the time I look at it. And by the way, it's already 32, and when I started to solve this problem it was only 30, so the number is grows. The people are just passing the first solution that they steal from somebody. So let me explain what I understood from this problem. The problem is to permute at exactly k position of all the permutations, and that means, so we have some letters, we put them in a frequency, and then we take one by one each letter. So we have positions, we have frequency equals some, for example, A, 3 letters, B, 4 letters, and so on, from A to Z, and then we take it one by one, and we try to place from A to Z for the first position, then for the second position, and so on. And to place it for the position, we kind of taking it, and we want to find what's left from this. And the number of permutations starting with this letter. So starting with, for example, we're taking letter, for this position, we're taking letter B. We removing this B from the frequency, and we computing how many permutations we have left on the suffix of all the positions we have. So this is a statistic problem. The number of permutations, if we have taken frequency of B, or just FB, It's a frequency we take. And how many permutations we have? Oh, not like that. So sorry. So we have left for all these positions. We have for suffix positions we have f new. So this is new frequency where we taking the f. We just did fb minus minus. So this is f new. So we have fa, fb, fc, and so on up to fz, and we have to compute how many permutations we have for if we take each letter one by one for this entire suffix. And the formula is that we're taking fa. So initially we have n is a f sum, so total what's left in the all positions we have, basically this entire length of what we have. And then we take in first a, so the number of permutations is n factorial divided by fa factorial, and this is what we take n minus fa. So this is statistics formula, and if it's just take a fa from the n, and this is how many permutations we could have after we take it. Permutations of all the others. So all others have this kind of number of permutations if we take fa. And after we take fa, we have to take fb, fc, and so on. So we have to go into our suffix and take all of them. So we kind of multiply it by n minus fa, because we're taking fa. Or basically we can say that we decreasing the number of leftovers n minus equal fa. Then we take like f n. Okay, this is again n fb n minus fb, and this is a factorial all the way. And again we take in this n minus equal fb. So this is n decreasing always, and we multiply it up to z. And this product is the number of all the permutations we could have if we started by taking fb minus minus, so from our position. And after we take it, we have this kind of p-value is count equal p it is permutations of all the frequencies we have, all the frequencies. So we're doing fb minus minus, then we take an f and p of f, and this is our count of how many permutations we have. And now we see that we have a k, and for k to be inside so we're taking it basically. How can we draw it? So take first and you inside k or outside k. I'm not sure how to draw it. So we have the 0 position, and we have number of permutations like infinite, or I would say very big number, and this is kth. And if we take, for example, a, and we see that it is inside, and then that means we what? This is where I did a mistake, by the way, because this is how you have to understand that if your count is inside you skipping. So if your count is inside is less than k, then you try b, and so on. This is what where I made a mistake. Basically, I assumed that I should be inside the from 0 to k, but it wasn't the case. You have to find the first character that the tail count is bigger or equal than k, and that means what your choice is that it would be less than k, but what you computing is you're computing the suffix. That means that's why you're comparing count to be bigger than k to be accepted as inside the 0kth range for the choice you made. Okay, this is a crucial understanding of, even after I studied this problem yesterday, I didn't pay much attention how this equation works exactly, because you can just think about, so this is how much permutations you have, and you have to be inside the case, so you're naturally writing it down like count less than k, then append. But this is the other way, opposite exactly, because this is a count for the suffix. You're computing b for your f frequency after you've taken this character. That's why your count should be bigger than k, because this is the only way that your count of what you take exactly is less, or less than k. Okay, the equal thing is also not very obvious for me, even right now. And the number of permutations. So I explained this formula. This can't be computed, cannot be easily computed, because this n factorial is too big for even for the long numbers or e64. You have to do the trick, and the trick is the maximum. Trick equals, you have a maximum of how many permutations you have, and this is exactly k, so no reason to continue to count this count of permutations if it is already bigger than k. Just assume that it is bigger, and this is be enough. So you have this you're taking each letter in the frequency, you're computing, this is a NCR or Pascal triangle, and this is number of permutations. And if it is bigger than maximum already, just return the maximum. And your maximum should be already bigger than k, so that's why you're taking it 1 plus k. And by the way, I also did memory limit exceeded solution trying to do with Pascal triangle, but the space and I think the time would be out of accepted range, because this is total f sum, it is just s length, and this is n square already. But given that we have this maximum, it's like a cheat code. It allows us to just compute it in a single loop operation. And at this time I just gave up and asked the AI to help me to overcome this, convert this Pascal triangle, and he proposed this one of memory solution. So the C equal, so this is a number of combinations to choose from n positions. We choose k or r, and this is choice total. How many you choose, your choice. Maybe I'm wrong because I don't know, this is very hard for me, and I understood it like this is just a row and this is just a column in a Pascal triangle. So a Pascal triangle is we have this triangle. It starts from 1, then we have 1 1, the next row is row 0, row 1, and then we taken the sum. So starting with 1, and then we taken the previous row of, and we taken left and right. So this works like this: 1 2 2 1. This is just a sum, or and it continues to be like that. 3, and then we take 4, then we take 3, and then we take 1. I hope I didn't make a mistake. Maybe yes, I made a mistake because this is not duplicate 2, it's just 1 2 single, because number of columns equal the row. This would be 1 3 3 1, so it is 1 2 1 in the previous row, and this is a CR. We have rows 0 1 2 3, and the result in the CR, this is a C of how many total we have is a row, and how many we choose is the column, and the column is 1 2 3. I'm not sure from where to start. I assume this is 3. So this is how choice, and this is equal to 3 factorial divided by, maybe I make it biggest mistake. This is 2 actually, because maybe it starts from 0. Yes, 1 2 3, and this is a 2 factorial. It is 3 minus 2 factorial. This is a choice number of permutations to choose this column count from this total row count. This is how Pascal triangle works, and when we compute on this, it is like CNR, and it is a sum of previous row and minus 1, left position column minus 1, plus C previous row current column. So this is a column, this is a row. Basically this is just x y coordinate, this is y coordinate, this is x coordinate. It's just notation. It's not very hard if you assume this is just 2 coordinates and that's all. But this is not just coordinates, it's coordinates in the Pascal triangle. Okay, and what makes it work is that I mean AI proposed to use just pre-compute it, like the count equals, it's just factorial, so n factorial, yep, divided by n minus I is factorial, n minus I. Hold on, this is not it. n minus I plus 1 divided by I. And this is and I grows from 1 up to R, like n is, if this is n, it goes n minus n plus 1 divided by n multiplied n minus 1 n minus n plus 1 plus 1. So this is hard for me. It's just math, nothing to think about for too long, because not for my brain. The people with big brains already solved everything that you need, and the future AI will make them out of work, even these people with big brains. So let's look at the shortest version of this code. Actually, fun stuff just starts with when you trying to make it short. This is what I like the most. Okay, and the shortest solution is actually almost 1500 milliseconds compared to the long solution is 40 milliseconds. And why is that? It's because we didn't stop when we reached the maximum for the permutations and for Pascal. We just continue to calculate the fold and just take minimum maximum each time. And this gives us 1500 milliseconds. And the same for Rust, by the way. It is 1200 milliseconds. So Rust is not a big deal if you make the algorithm slow. And the Rust optimal solution, when you return early as soon as you reach the maximum, is only 7 milliseconds. This is where the Rust shines. It's compared to the 43 milliseconds in Kotlin. Okay, that's it for today.